Hey everybody, and welcome to unit number 9. We are discussing neuroplasticity today. So we're going to be talking about what happens in the brain whenever we form memories. And I know that sounds very complex, and it is, and it sounds maybe a little bit intimidating, but I'm keeping in mind that not everybody in this class has taken behavioral neuroscience with Dr. Manella. So I know that we all come into this with different backgrounds, so I'm going to try to keep this mostly self-contained. I'm not going to go into a lot of details about neurotransmission and stuff like that. So we'll kind of give it a broad overview, look at what happens in the brain when we form new memories, and yeah, so I don't think this will be a super long video like some of the previous ones were. So let's just go ahead and get right into it. So what is in this unit? We're going to be looking at some of the building blocks of memories, but specifically what's going on in the brain whenever those memories are formed. So the past couple of units we talked about classical conditioning, and we talked about sensitization and habituation and things like that. Now we're looking at what changes are taking place in the brain whenever those things are occurring. So we're going to be looking at the neuron and its basic anatomy and how those pieces of the neuron interact with one another. We'll be talking about what changes during classical conditioning, what changes during generalization and discrimination, and how all of this feeds into long-term memory. So let's get into it. I wanted to start here because I know a lot of psych students, not to go on a tangent, but I know that a lot of psych students feel like that this is the area of psychology they're not super excited about. And I know that because I teach the basic process courses in our major, which are cognitive psychology, sensation and perception, and those are usually the classes that people are like, I didn't sign up for this because I wanted to learn about this. I wanted to be a psych major because I wanted to be a clinician or a therapist or whatever, right? So I understand that this stuff can be a little bit dry for a lot of folks. But with that being said, this is why I wanted to start here, because I think that this is a great entryway to be thinking about this material that probably all of you can relate to in some degree. Alright, so let's talk about Hebb. Hebb is this guy, Donald Hebb, a key, very important, crucial figure in neuroscience, specifically in neuropsychology. And he, if I am mistaken, he's a Canadian guy, or he was a Canadian guy. We're going to see this guy again because he was super influential in this field. But I wanted to start here because he has this really fun, interesting study where he found that rats that are raised as pets typically would do better in performance-based tasks than rats that were raised in a laboratory setting where they have ultimate control over the environment. And this honestly kind of flew in the face of a lot of research at the time, because the idea was that we're going to train non-humans in a laboratory setting so that way we can control what things they're exposed to, and as a result they should be really good at the tasks that we give them. Here we're talking about mazes and things like that. But what Hebb showed is that if you were to raise a rat, as a pet, give it lots of attention, play around with it, in the afternoons or whatever, that those rats, even though they didn't have very tightly controlled environments, those rats actually did better for these kind of quote-unquote cognitive tests, like mazes and things like that. And the question is, well, why is that? Why do you think that is? You might give me some kind of gushy, ooey-gooey answer by saying like, oh, well, it's because you loved the rat, and the rat, understood that you loved it, and so it, challenged itself to do the maze, or whatever. You don't really believe that, right? You don't really believe that the rat was inspired or something like that because it was treated like a pet. Or at least I'm not so sure I buy that. I don't see the evidence for that. So what Hebb suggested was that not only is their behavior different, but after they passed away, he was able to do an autopsy on these rats, look at their brains, and basically found that their brains were quite different too, and they were different at a cellular level. That those neurons in the brain of the rats that were pets were fundamentally different than the rats that were not like that. here is an extension of that research. And so this is, way back in the 70s whenever Hebb was initially studying this, and people have been studying it ever since. And we call this enrichment. The idea about enrichment is that if you give something, and we're not going to say this is a human, this could be anybody, it could be a human or a non-human, that if you're giving some organism extra care and attention and opportunities to interact with its environment, that actually serves as a positive thing on the neural development of those organisms. Now, that seems really obvious whenever you apply it to humans, right? That humans thrive whenever they have lots of opportunities, whenever they can interact with lots of things growing up, that they're not just isolated or neglected, that it can be helpful for to have love and attention especially. Love especially too. They're both good. But that this enrichment actually changes the cellular structure of neurons that form the brain. So here is a more recent study. It's not super recent. It's over 10 years ago. But and I wanted to assign this one for this unit because it's a really crucial, interesting article. But I thought it might be just as interesting to kind of just show you the quick kind of slice of it, because it's an insanely detailed article. So even just trying to read this, effects of daily environmental enrichment on behavior and dendritic spine density in hippocampus following neonatal hypoxia ischemia in the rat. That's a lot. But basically what they're trying to show here is that they had two groups of rats. One group that was in a high enrichment setting and one group that was in a low enrichment setting. The high enrichment setting basically meant they had toys to play with and puzzles to solve whenever they weren't doing anything related to the research that they were involved in. Basically gave them extra things they could interact with. And what we see here, what they're measuring when they're talking about this dendritic spine density, they're looking at in a cell down here at the end. Whenever we are talking about the ending part of that neuron, you zoom in on it and you see these little spines. Well, if you are in a low enrichment setting, in other words, you don't have a lot of opportunities, you don't have a lot of things to interact with, what we see is that there's not a lot of dendritic spines there, right? It's mostly just the dendrite and none of these receptors on the end. If we look over here with the high enrichment group, so the group that did get lots of environmental enrichment, so they got lots of toys and things to interact with and play with, and it can even be social, it can even be allowing these rats to socialize with one another, that actually changes the structure of those neurons. You can see all these tiny little receptors growing out of that dendrite. So why is this important? Basically this shows us that whenever we are talking about how things develop, that we want, in order for our brains to be in the best shape, we want to have environmental enrichment. We want to have opportunities to interact with the environment. We want to have new things to explore. We want to have things that we can interact with, we can play with, that we can manipulate and problem solve and interact with others and things like that. All those things are important, not just because they make us feel good, but because they do have a measurable impact on the connectivity of the brain. So now we looked at the big picture. Now let's focus in, look at some of the specifics here. So the structure of the neurons were different after enrichment occurred. So this is, maybe it's because of playing, problem solving, or other kind of fun activities that we have here. And you can easily imagine extending this to human beings, right? That a human child is probably going to be at their most well-rounded whenever we give them lots of, not toys, but lots of things that they can learn from. Things that, maybe puzzles that they can play with and try to learn critical reasoning skills, or that we give them multiple exposures to different kinds of books and things like that to give them new ideas and new perspectives on the world. All of these things fall under this category of enrichment, and these things are really important whenever our brain is developing and getting more and more complex. So basically, in that study, what we saw is that the number of dendrites increased. So not just the length of them, but also the total number of counts. And why is that important? Because dendrites are the part of the neuron that is looking for incoming neurotransmitters. It also results in a larger volume of the mitochondria in each cell as well. So you remember the mitochondria, right? You remember that from high school. It's the powerhouse of the cell. It is the part of the cell that I think is also responsible for RNA, but it's a very pivotal, very important part of the cell. And just through environmental enrichment like this, we see that the mitochondria strengthen over time. And then finally, the volume of glial cells also increases too. If you're not familiar with glial cells are the fatty tissue that surrounds the longest part of a neuron that helps conduct the signal so that that signal doesn't get lost as an electrical impulse is traveling from point A to point B. Okay, maybe that was a lot, right? Especially if you haven't taken behavioral neuroscience, maybe you're feeling a little bit lost. You're like, what the heck is a glial cell? Let's back up. Let's take a deep dive on the neuron. So here we have a typical neuron. It looks kind of similar to what I showed you earlier. But I want to kind of walk through this because some of you may not, if you haven't had me for cognitive or Dr. Manella for behavioral neuroscience, maybe you haven't seen one of these friendly neurons in a couple of years now. So let's talk about what this is. Our central nervous system is made up of these things. It's in our spine, it's all throughout our flesh, but our brain is mostly neurons and fat. It is, our nervous system is made of this stuff. And these neurons have three different functions. They collect information that's incoming, they transmit information, so they're going to send information, and they're also going to process/integrate information. Okay, what does this mean? It's all very vague. What this means, and I'm going to point over at this neuron to kind of explain here, it collects information. Basically, in these dendrites over here, at the top over here, these dendrites are hungry, looking for neurotransmitters. Neurotransmitters like dopamine, serotonin, acetylcholine, GABA, norepinephrine, all the ones that you've heard of before. So it is glutamate. It is all these dendrites are thirsty for those neurotransmitters. It's looking for incoming neurotransmitters. So, and you can see why like having more of these can be helpful in forging new connections. The more dendrites you have, the better chance you have at collecting incoming neurotransmitters from from other neurons. So these dendrites are going to collect information, neurotransmitters. If we collect enough of a specific kind of neurotransmitter, then that cell is going to make the decision, that's, I'm putting that in quotes there, to integrate that information and to fire an action potential. That action potential, and this takes place over here. So basically we get enough neurotransmitters up here, and this cell is going to decide that it is going to send an action potential, and that is a very complex reaction. And it takes place basically at the blink of an eye, but it's a really, really complex thing. You can ask, anybody who's taking behavioral neuroscience knows this because you talk about sodium ions and potassium ions and sodium pumps and stuff like that. You talk about that stuff for like weeks and weeks on end, right? So it's all of this stuff, is really, really complex. But basically, this cell is going to decide when it gets enough of those neurotransmitters to fire an action potential. An action potential is going to be the electrical signal that conducts itself to the end of the neuron, so that way that neuron will create neurotransmitters by itself, so that the next neuron in line can get those neurotransmitters and continue sending the signal until it gets to the end point. So that decision to fire an action potential, an electrical signal, that is processing/integrating information, and then after that, that signal is going to move from the cell body down the length of this axon all the way down to these terminal buttons. Sometimes people will call them axon terminals. Either way is fine. But basically, in these little spots down here, they have vesicles that are filled with neurotransmitters, so that whenever they are stimulated by that incoming electrical impulse, they're going to release neurotransmitters as well. And then that way it's going to float across the synapse and then activate the next neuron in line. Or at least theoretically, that's what happens. So we have these basic components. We got the dendrites. Those are what receive incoming information, incoming neurotransmitters. We have the cell body, which is sometimes referred to as the soma. The cell body is going to be this area right here, which is going to manage when we send an electrical signal down the length of this axon. The axon, which is going to be just this, it's just basically a tunnel that the electrical signal travels down. That's its whole purpose, is to help make that that electrical impulse travel. And then finally we have the axon terminals, or the terminal buttons, and these are these buttons at the very end of the axon that have neurotransmitters, and whenever they are stimulated, they're going to release neurotransmitters for the next neuron. So I've mentioned a lot about electric impulses here. Are neurons, are they more chemically focused or electrical focused? They're actually both. So the action potentials that I referred to, those are electric. So that is an electric, usually about negative 70 millivolts, I believe, that travels down the length of an axon. The chemical side of things, that's going to be the neurotransmitters. The neurotransmitters are chemical in nature, which basically is, we have these molecules that are binding to the dendrites. So whenever we ask about how the brain works, it's both. It's both an electrical mechanism and also a chemical mechanism. So we can have excitatory neurotransmitters, which means that that cell, that incoming neurotransmitter, is going to be more likely to fire, but we also have inhibitory responses, which means that that action potential is going to be less likely to fire. And we've used some of this language already this semester, especially in the past couple of weeks. So if you are, have been a little bit stuck on some of those research articles, you can check out, maybe this might explain a little bit about the sea slug and about if it's releasing neurotransmitters or not. And what happens whenever we stimulate part of a sea slug. Does that lead to an inhibitory response or an excitatory response? This is what all this is referring to. So between the neurons, we have this gap, and this gap is called the synapse. One very common misunderstanding about neuroscience is that people think that the synapse is a structure. It's not really a structure. It's an area between two neurons, or more neurons. And it's in this area that these neurotransmitters are going to be moving from the terminal button, or the axon terminals, over to the next neuron, which is going to be the dendrite side. So we have the presynaptic location, which basically means this is before we create the neurotransmitters, and then we have the postsynaptic, which basically means after those neurotransmitters are created. So basically the presynaptic side is going to be the axon terminals, and then the postsynaptic side is going to be the dendrites. So here is a collection of 9 neurotransmitters. Now there's more than 9, there's more than 20, I believe. I don't remember. I wish I could tell off the top of my head. I want to say it was like 20 something. At least that's what it was in grad school. So who knows? It could be different by now. But here are the 9 big ones, I would say. The 9 that that a lot of people know. And so if you're a psych major, you should get these tattooed on your arm or something like that to remember what they are and what they're for. Probably the most common that people talk about are serotonin and dopamine, because people will talk about if you're low on serotonin, it puts you in a bad mood or something like that. And yes, serotonin is related to mood, but it's also related to sleep, it's also related to how much you eat, and it's also related to aggression. So it's related with more than just, feeling good. And for dopamine, that's going to be for a lot of operant conditioning and a lot of reward-seeking behavior. So learning to get, if you do something that you're going to get rewarded for it, that's what dopamine helps us with. But we also have glutamate, we got GABA. I didn't mention GABA earlier, and GABA is a really big, important one. We got acetylcholine, which is going to be used for a lot of motor and muscle-based kinds of reactions. Norepinephrine, you can kind of think about this as noradrenaline if you want to. And this is going to increase arousal and also help boost long-lasting memories. Don't forget about that. And so on and so forth. So we got these different neurotransmitters that are sometimes going to be involved in memory formation. Now there are 6 things that I want us to keep in mind as we move forward. So 6 things that are like good principles of the brain and how the brain is able to change over time. So the first here is that neurons are flexible. What does that mean? Does that mean they can do a back handspring? Does that mean they can stand on their head or do really complex yoga positions? No, it just means that neurons can change over time. So neurons are not set in stone. Doesn't matter how old you are. If you're 97 years old, then your neurons are not going to be static. They're not going to be that way forever. They are going to change just like you change. So the first piece, neurons are flexible. The second piece, connections between neurons can strengthen over time or weaken over time. So you got 2 neurons that are close by. They can get stronger or they can get weaker. The stronger they get, basically what that means is that those connections are used more frequently, and because they're used more frequently, they get stronger. So you have these 2 neurons. If they are used a lot together, then they're eventually going to get really, really close to one another, or their dendrites and axon terminals are going to get closer together, and it's going to be more efficient in conveying that signal. What do I mean by that? If you're looking at this figure right here, these neurotransmitters that are hanging out in the synapse, some of them don't make it to the next neuron. A lot of them will just kind of drift in the synapse and then just fade away because they get broken down by other enzymes. And this is actually, not to go into too much detail, but if you've ever heard of like an SSRI, that is a selective serotonin reuptake inhibitor. So what the heck does that mean? Reuptake inhibitor. In other words, they're going to try to stop your neurons from reuptaking. So we got these neurotransmitters that are floating around in the synapse here. Not all of them are going to make it. Some of them, if they're out here long enough, are going to get broken down by enzymes. And basically, what these reuptake inhibitors do is they stop or reduce those neurotransmitters from coming back into the cell. Those that are, if you have too much, they can be reabsorbed back into the cell. And what SSRIs do is that they actually block that mechanism from happening, trying to force that serotonin that your body is making to not just get reabsorbed, but to eventually make its way to the next neuron. So whenever these connections get stronger, it basically means that there's less neurotransmitters that are getting wasted because those connections get very, very efficient. If the connections aren't used, then those connections are going to weaken over time. So if you're not using it, then they grow apart and it's harder for them to communicate as a result. New connections are made all the time, as I mentioned. It doesn't matter what your age is, and also that neurons don't live forever. So some neurons can die over time. And I think, like every 7 years or so, every single cell in our body will eventually recycle and like die off, and then a new one is reborn in its place. All those neurons do that too. So sometimes just over the course of years or decades, those neurons don't live forever, and that can impact our ability to retain memories. If one of those neurons in that complex network is not responding because it has died off or been pruned away, that can absolutely affect what we remember. So these ideas are going to factor in how memories are created and also how we are able to form habits and things like that. So let's talk about the brain a little bit. We've been talking about the neurons specifically. Let's kind of zoom out a little bit to talk about how the brain is plastic. Basically, the brain is constantly rewiring itself based on your experiences. And this is, I find this to be super profound because I think we think about this metaphorically a lot, that whenever you learn something, that you learn a really important lesson, and something about you changes. You've grown up. You've matured in some way. But that actually happens whenever you learn something. Whenever you learn anything, that brain is going to rewire itself in different ways. And that's what we mean by neuroplasticity. That those brains are rewiring itself so they are not stone. They are much more like plastic, where they can be molded into new things. And so based on our experiences, whether or not these neurons are going to fire a lot together or if they are going to not fire together, that means that there is going to be either more or less neurotransmitters or more or less receptors. So our brain is going to, for some of these neurons, are going to get really close, those synapses are going to get smaller, and as a result they get more efficient in conveying whatever information they are trying to convey. Maybe it's pain, hey, I'm hurt, or maybe it's, oh man, I feel great, or maybe it's, what is that person doing? Whatever that information that you're trying to think about, it is all subject to your previous experience with these neurons together. So over here on the right, I know you can't see some of this, but you can just kind of see like all the different ways that a neuron can get better or worse at sending a signal and how this changes over time. So over time, we might have that this area of the axon terminal gets bigger. If it does, that probably means that it's going to be better at communicating its message to the neighboring neuron. We're also seeing that the contact zones, so these areas where neurotransmitters are let loose, that they seem to be a little bit more dense. The synaptic cleft, so this area between between these two, can change over time, and so on and so forth. These things change all the time. I told you we talk about Donald Hebb again. So Donald Hebb, this Canadian guy, some people consider him like the father of cognitive neuroscience or behavioral neuroscience because his impact was that big, which is weird because I feel like you don't really hear about him all that much in psychology, right? You hear about Pavlov, you hear about Watson, but you don't really hear about like, well, who made all the differences, when it comes to brain science, that really important part of our major. Donald Hebb, I would say, is a good bet for that person. Donald Hebb is everything we just talked about, those 6 important principles, that all came out of his work. He was really interested in how cells change over time based on our experience. And so he would phrase things like this: cells that fire together, wire together. Whenever you hear that, basically what that means is that you have 2 cells that are nearby one another, and if they are firing together, then they are going to slowly start cooperating with one another. And so, according to Donald Hebb, learning was really just kind of how efficient are your synapses. If your synapses are very efficient, in other words, there's not enough neurotransmitters that get lost in those synapses, that means that you have learned things really well. So here is a great quote from Donald Hebb. When an axon of cell A is near enough to excite a cell B and repeatedly or persistently takes part in firing it, some growth process or metabolic change takes place in one or both sides, both cells, such that A's efficiency as one of the cells firing B is increased. Which just says what I was just mentioning, but is also kind of boring, also kind of hard, maybe kind of complex to understand, and maybe that's why he's not as well known as Watson and Skinner in our field. So to put this in kind of foolproof language, basically what he's saying is that as neurons are used together, the communication between those neurons is easier. And we can look at Eric Kandel's sea slug's work as evidence for this. We can actually look, because those neurons are pretty big and there's only a few of them, relatively speaking, for these sea slugs, that we can look at behavior changing the brain in real time. We can see how poking a sea slug changes its neural makeup, its brain chemistry. And it doesn't have a brain the same way that we think about brains, but you get the idea. So there are 2 different kinds of neuroplasticity when it comes to memory. The first is long-term potentiation. Long-term potentiation is generally, I think a lot of people kind of point to this as this is the origin of long-term memory. Long-term potentiation is. So whenever you have 2 neurons that are firing together at the same time, those synapses get stronger and more efficient. Exactly what we've been saying. And that, according to most folks, is the basis for long-term memory. And this is part of the reason why things that or events and information that we think about a lot, those stand a good chance of getting into our memory, because it's like we're thinking about that information more, and because of that, the neurons that are nearby helping us make those thought patterns are getting closer to closer, and they're getting more and more efficient. Long-term depression is kind of the exact opposite. Whenever you're not thinking about something, you're neglecting it, you're ignoring it, that the cells that typically would otherwise be communicating about that stimulus are going to grow apart, and so it's harder for them to strike up a conversation now. So in the long term, both of these things are going to happen to kind of help us restructure our neurons so they can communicate more efficiently based on our environment and based on what we interact with around us. So you can think of long-term potentiation as sprouting new synaptic contacts between similar neurons, and LTD is whenever you are essentially kind of pruning away and stripping back some of those dendrites and axon terminals because they don't seem like they're being used as much as they were before. So in order for neuroplasticity this just kind of reiterates what I was saying here, is that neuroplasticity is kind of the basis for learning and memory. More specifically, probably long-term potentiation is a really big player here too. But one of the important lessons of this chapter is that experience is going to help us change that. So as much as psychologists we like to focus on behavior instead of brain stuff because we can see behavior, I do want to make sure that we all are on the same page, that these things are very closely linked together, that a change in your behavior is going to result in changes in the brain, and changes in the brain are going to result in changes in behavior. Alright, so in this example, let's say that we have rats that are raised in an enriched environment, so these neurons are going to give us more synaptic contacts. This is what you're seeing here, where you got rats that are in a standard laboratory setting versus an enriched laboratory environment. And in this case, they let them play with toys in their cages, and they also would have these social meetings where like they would let rats interact with one another. And you can see that there's a pretty moderate difference in the total presentation of these neurons. There are just more connections that can be made for the enriched laboratory environment because of how many dendrites and axon terminals you have. So you have, it looks like a lot more, and they kind of reach off a little bit further out too, which is all things that can affect how we remember the world around us. So let's take a look at how these areas of the brain are reacting together. And we'll first do this by talking about classical conditioning. So here we're going to focus on the cerebellum for a moment. And that is actually kind of weird because, at least in cognitive psychology, we don't really talk about the cerebellum all that much. And in fact, for the longest time, people just assumed that the cerebellum was used for balance and that it was used for essentially coordination. And then, like, I don't know, a little over 10 years ago, a young woman was discovered as being born without a hippocampus. Not a hippocampus, a cerebellum. She lived her life without this big hunk of broccoli, this broccoli-looking structure back here in the brain. So you can live without it. You'd probably be pretty clumsy, but you could live without it. But that's where we're starting here when we're talking about specific structures of the brain. So for the cerebellum, some basic conditioning tasks are going to rely on the cerebellum. And this area is considered very basic. As you may know, essentially the deeper you get in the brain, the more primitive, the more survival based a lot of those structures are. So when we're talking about like how the brain monitors heart rate and breathing, a lot of that stuff is going to be very, very deep in here and not necessarily on the surface. So when we are talking about the kinds of things that the cerebellum is responsible for, just keep that in mind, that the cerebellum is pretty deep inside the brain. We're talking about very simple kinds of rudimentary behaviors for the most part. So when we do classical conditioning tasks, we see that the cerebellum is activated. It is one of those areas here. And we can see that here with what's called the Purkinje cells. The Purkinje cell is a very specific type of neuron. And what you see here, there's a lot to unpack here, so I apologize. So here, the x-axis, you have time, and time is going to just go on as a matter of course. Here we have a tone, so this tone would be a conditioned stimulus where you're probably going to be hearing, I want to say here, which is a beeping sound. And then here, the unconditioned stimulus, as you may remember, is a stimulus that is going to immediately trigger a response in you. You don't need to learn it. And here's an air puff. Basically, they blow a little bit of air in somebody's eyes and they watch them blink. So, what you're looking at here is a tone is being made, and then we have the unconditioned stimulus that is going to occur. So you can think of this tone almost as like a warning sign. Like, hey, you should watch out. There's going to be a puff of air that gets blown in your face. Over here on the y-axis, this is what's called a raster plot. Actually, I'll write that out. It's a raster plot. And what you have in these black lines, these are how many action potentials were fired. So the more, the better. The more, the taller these pieces, it basically means the more that somebody's cells were firing. Excuse me. I had a hiccup again. And so, basically, if you see this trend, your Purkinje cells are working at their baseline rate. Then we hear that tone that lets us know that we're about to have air blown in our face, and you see it drop. You see those Purkinje cells are going to be activated less. Then we have the unconditioned stimulus, and then it kind of goes back up to baseline. So what does that mean? I don't know. You tell me. But basically what we're saying here is that there are certain cells in the cerebellum that are sensitive to classical conditioning. That we can look and see how this one cell, when we were presented with the danger symbol, it essentially kind of turned off. That this area of the brain was like, I don't want to deal with this. It's too traumatic or something like that. So conditioned responses, like what we would see here, let's say that closing your eyes would be the conditioned response of having an air puff blown in it over and over and over again. So this conditioned response is modulated by another structure as well, and that's the interpositus nucleus. The interpositus nucleus actually doesn't come up that much. Yeah, I don't know what to tell you about that. I was going to say, I'll tell you everything I know about the interpositus nucleus. It's very nondescript. And it's a deep brain structure. So it's not one that's going to be used in like higher order cognition, like language or problem solving or love or anything like that. We can put lesions in the cerebellum. So a lesion is like we can like make a cut or damage a small part of it. And if we do, then what happens is that people will start what changes, what's affected is the conditioning that takes place after this. So if you have lesions in your cerebellum, it takes you longer to learn classical conditioning, longer to learn the paired associations between stimuli than if you didn't have this area damaged or removed. And then finally we have the removal of the hippocampus results in an elimination of latent inhibition. Oh man, what does latent inhibition mean? You may remember that from Dr. Reyes' learning class. Basically, latent inhibition would be like, let's say, I used aversive conditioning last chapter where I was asking you to think about things like throwing up to make my point. So what is latent inhibition? Let's say that you go out and you get your favorite food, which is, I don't know, a Big Mac or something like that. And then one day you eat a lot of these. You eat them like a couple of times a week, and then one day you go to eat one and you start feeling sick and you throw up. Do you think that you will eat a Big Mac again? You will. You will eat a Big Mac again. It may take a while before you feel like you can do that, but that would be an example of latent inhibition. You've had sushi other times in the past that went relatively well, and so what you've learned is that sushi is not bad. That sushi is food and that it's interesting, yeah. So latent inhibition is this idea that like sometimes learning can take place a little bit more slowly depending on what we've learned in the past, and those things in the past can influence our behavior in the present. Yeah, so removing the hippocampus means that you lose the ability to make latent inhibition judgments where you're not 100% sure if this is the very first time you've tried something or the 30th time you've tried something. So learning isn't impossible. So if you haven't already, definitely check out Dr. Reyes's capstone class that he's offering. Alright, so here is a fun article that David Knight from the University of Alabama, Birmingham put together. And so in this study, basically he was interested in a couple of areas. One is the amygdala, and the other is the prefrontal cortex, and the other is the hippocampus. So he was interested in specifically post-traumatic stress disorder. And so the task that he gave people is that he played an unpleasant burst of white noise. So, you know, like you turn on TV and it's just static, or a radio and it's just static. So that idea right there. So participants had to try to tell us, when do we expect that sound to occur? And so what you're looking at here is the rating bar where they rated, you know, like how likely was I to miss something, to overlook something. Also, meanwhile, participants are also having their GSR measured, their galvanic skin response, which is a measurement of stress. So just to recap, we have people that are doing this task that are expecting white wine. They're expecting to do some wine tasting. But we also have that maybe one of the biggest, most helpful kind of ways that we can measure physiological data also backs this up too. So, yeah, is there anything else that I want to mention here? Basically, they're going to be looking at whenever people are trying to predict when this unpleasant burst of white noise occurs, can they predict it, and does their body react to it? So they're going to consciously tell us, no, I could not predict it, or yes, I knew that that really unpleasant sound was just about to occur. And they measured people while they were in an MRI machine. Alright, lots of data here. Let us unpack it piece by piece. Let's look at the unperceived. Let's start here. Basically, we're looking at the times that people couldn't figure out the pattern of what signal meant they were about to get hit with a white noise burst. So that's all the people that we see in unperceived. Now, CS plus, this black bar, basically means that yes, that unpleasant noise is coming. The gray bar means that no, the unpleasant noise is not coming. And so we can see that in terms of expectancy, so how well they did the task, basically no difference between these two. It didn't matter if somebody had I lost my train of thought. It wouldn't matter if somebody could predict it or not, if they were conscious of it. And then we also see, when we're talking about the skin conductance response, we're talking about physiologically, how tense are they? We do see a difference there, though, right? So we see that the CS minus folks, they're pretty chill, because the higher this is, the more stressed you are, the lower it is, the less stressed you are. So there's a pretty big difference between gray, which is chilling like a villain, is feeling totally safe, versus this bar right here, which seems to know that something is coming. Now, the reason why that's important and the reason why it's interesting is because this is unperceived, that the participants could not say, yes, I knew that I was about to get hit with white noise, right? So they weren't able to say what the pattern was, but their body had learned it. And that's what I'm trying to point out here, is that the body learned, oh, we have the CS plus coming up. In the past, that CS plus is followed by white noise, so I'm going to go ahead and start getting a little bit on edge and get a little bit prepared for this. So, let's take a look now at this second half here, where we're looking at the perceived folks. So these are the people who correctly perceived that the white noise was about to occur. And so what we find here is that, yes, they are really, really good at identifying it, above 80% chance. So they're good at knowing what signals are going to lead to white noise and which ones aren't. And then down here, we have, for the CS minus, a pretty big difference, right? So these folks weren't quite sure, but they were okay in terms of getting this right. And then finally down here, we have the skin conductance response, and we see that the people who knew that the shock was coming were more tensed out compared to the group that did not know it was coming, which is probably not a super big surprise. So basically what we can draw from this, and the reason why I think this is a fascinating study is because what it shows is that the body seems to recognize some kind of pattern before we can verbally say what it is. And the evidence for that is what we see right here. That basically, even though participants said they could not perceive a difference between these groups, that just from hanging out, that these things change over time, whether you're consciously aware or not. All right, I don't know. I don't want to talk about this too much, but we see that whenever people are learning this task, that we have the middle occipital gyrus seems to be a very commonly activated area, which is kind of interesting because you don't really see the middle occipital gyrus shouted out all that much in your other classes. All right, let's talk about what happens with generalization and discrimination whenever we are learning new things. Right, so let's look at what happens at a very specific neuron-based level here. So this is basically a generalization gradient, but for a single neuron. So what exactly does that mean? Basically what I mean is that this specific range, and we're looking at sound in this particular example, that whenever a sound is presented, that this neuron is going to be firing basically at its height up here, but it's still going to be mostly active anytime it's presented with a sound right here. Does that make sense? So if you have a sound that is lower than this, that cell is not really activated. If it's higher than this, it's not really activated here. There's this sweet spot right here. And what we're going to look at is how this can actually change with experience. That this is something that can change based on the associations that we make or how we've been incentivized. Okay, let me show you what that looks like. So first, we can see how this is correlated with the behavior. You may remember this from last unit. We were talking about generalization gradients. So this would be like if we had trained up looking at yellow, that whenever we are exposed to a yellowish green, which is kind of similar, we're going to have a similar kind of response. It's still going to be somewhat of a response. It's not nearly as high as our peak response, but we'll have a moderate response, and that's kind of what we have over here. So in this case, we have this specific neuron is tuned at its most right here, and then as we move in either direction, it kind of falls off. But the reason why I wanted to show you this is just partly to show you this kind of normal distribution. If you've taken stats, you know what I mean by normal distribution, where it's kind of goes up and then kind of goes down like that. We have this just like that, and this shape can actually change over time. So let's talk about that. Let's talk about how we can. I'm going to skip this slide right here actually. So we can actually change the way that, and this is what you're looking at right here in this orange figure, in this orange line. This is the previous line that we just saw. So this would be like before training to hear this 2500 hertz Q tone, which is right around here. That's what we're listening for. And this neuron used to be, right, it was mostly just active in these ranges right here. So yes, it is going to be able to detect and pick up this 2500 hertz sound. But after we have some training where whenever we experience this, we know like that something is going to happen as a result of that. Maybe we get some food, maybe we get an electric shock or whatever, but we learn that it's predictive. What happens is that gradient for when it fires or how strongly it fires is actually going to shift. And so this orange is now going to shift to the purple, which you can see here, which is totally different, right? Basically, we had this orange shift over to the right so that it is now maximally sensitive to that specific cue. So basically, this neuron, with enough training, with enough experience, has now kind of shifted its priority so that it's now going to fire when it hears this specific sound instead of this specific sound over here. Here, and this is kind of what it would look like if we were looking at behavioral generalization. If we were, playing like a specific sound during regular training. This is, kind of what we saw before, where we have kind of this normal distribution. It goes up, then it goes down like this. Pretty standard. But over time, if you were to practice a discrimination training task where you teach, the organism that if you peck, or I say peck because it says peck here and it's referring to pigeons, but if you respond a certain way whenever you hear this tone, you get a reward, but a very close nearby tone, if you hear that, you're not going to get rewarded for that. What we see is that this broad purple is now going to get really constricted. It's going to get very, very thin here. And the same is true for the neuron that underlies this. That neuron's receptive field is also going to shrink so that it can better discriminate those really tight frequencies there. So the neuron's receptive fields are going to change over time with experience there. All right, and so the cortex, just to back up a little bit here. Oh, because I didn't mention this piece right here, and I should have. Down here, here we're looking at neurons in the auditory cortex. So these are neurons that are going to be responsible for helping us hear, and that changes over time. If we were to just go through and just totally damage the primary auditory cortex, then we wouldn't be able to discriminate against different tones, because these neurons that help us kind of manage that and change that over time and with experience are going to be destroyed, and so we can't learn to discriminate different sounds. But the reason why I wanted to transition from here to the next slide is because now we're focusing on the cortex, and the cortex is just the overall outside, layer of the brain, and that is where a lot of our long-term memories are stored, is in the cortex, all throughout our brain, depending on what kind of sense we're paying attention to. If it's an auditory sense, it's going to be in the primary auditory cortex. If it is a visual sense, it's going to be in the occipital lobe. All right. So as we continue to experience these things, whether it be through training or through practice or whatever, the way that cortex is organized is also going to change. So whenever we habituate to things, the cortical space that is typically devoted to that specific stimulus, let's say that we're talking about a pitch in this case, so if you hear like a high-pitched humming sound from your TV or something like that, after time you block it out, and especially if it's been days or weeks or months that you have it on and you just stop paying attention to it, that will actually be reflected in the cortex. That there's going to be less area in the cortex now devoted to perceiving that specific pitch. And in terms of fear conditioning, when we learn that a certain tone predicts that something aversive is going to happen, we are going to expand the area of the brain that is dedicated to processing that specific pitch, that cue that let us know that something scary was on the way. So in other words, the whole layout of the brain and the way that it's organized can change based on our experience and our training with things. We see this a lot, especially with or I feel like maybe it's a really easy go-to example with musicians. I think maybe now's a good time to talk about it. I was looking for a good place to talk about it, but there's a really great research article that shows people that play violin. And if you play violin, think about how you hold a violin. You hold it, with your chin right up here. You got your left hand that's going to, be like fingering the strings and finding, the right notes. And then in your right hand you have a bow, and that bow is going to move back and forth like this. So what we find in people that are that practice a lot of violin is that the cortex responsible for their left fingers are going to be expanded. There's more space in their cortex responsible for processing the finger movements of their left hand compared to their right hand. Why is that? Because their left hand is the one that's doing all the moving, and that's the one that has to remember where things are. The right hand is just going to be moving back and forth, or maybe even occasionally plucking a string, but the fingers are not the important part of that equation like it is for the left hand. And so we have differences in hemispheres for the same area. where in one hemisphere, in the right hemisphere, which controls the left hand, those areas are going to be expanded, and in the left hemisphere, which controls the right hand, is not going to be as much. All right, winding down now, let's talk a little bit about the hippocampus here. The hippocampus, as we mentioned, is going to be is really helpful for helping us learn how we consolidate memories. And we talked about latent inhibition earlier, but the hippocampus is going to play a really important cue in helping forge a relationship between areas of our brain and the sensory cues that we learn about. So if you have hippocampal damage, then whenever stimuli are presented separately from one another, you don't really learn that they go together. So if I were to play a tone and then I shock you shortly after that tone stops, if you have damage in your hippocampus, you might be unable to learn that sound means that a shock is coming. That's the power of the hippocampus. The hippocampus is going to help us take this information and help store it somewhere so that we can draw a relationship between those two stimuli. So in the example that I gave here about, eating your favorite food, so like let's say if you eat your favorite food and you get sick, it's highly unlikely that you're going to develop some kind of taste aversion to that specific stimulus. And the reason for that is because you have maybe even years of experience eating that specific food and not getting sick. And so you're learning, hey, this food does not make me sick. And so that by the time you finally do get sick, you might get a little bit of a taste aversion, but usually not very much taste aversion to that. Yeah, I was going to give you a really gross example about a time that I got sick, but I'm not going to do that. I'm not going to put you through that. Your imagination works well enough. If we have hippocampal damage, though, this doesn't really work so well. Basically, if I have my favorite food and I have hippocampus damage and I get sick, then the next time I see that food or smell that food, I'm going to feel sick because latent inhibition is impaired when we don't have a hippocampus here. And that's it for this chapter. If you have any questions about some of these things, let me know. But really, what I want you to extract from this chapter, the most important stuff, I'm gonna say. Well, it's a little bit further back than I thought. Are these 6 things to think about. These 6 principles of the brain and of the neurons that make up the brain, they change with time, so they are flexible. They can change their connections. The connections can get stronger or weaker. If a connection is used more frequently, it gets stronger. If a connection is used less frequently, it gets weaker. New connections are made constantly throughout our lifespan, and that these neurons don't live forever, that they can naturally die off and be replaced by other neurons, which might affect our memory for those things because those connections are now slightly different because some of those neurons have died. Then that's it. The rest of this, we're talking about expertise coming up in the next unit, which is really, really fun. I feel like it's a really great gap or a really great bridge because we've been talking the past couple of units about these really nitty-gritty, microscopic kinds of memory formations, and now we're going to take another long view, and then for the rest of the semester, we're going to be looking at kind of really complex, interesting forms of memory that are, I think I would call it higher order. So it's, complex memories, not just basic memories for associations. All right, if you were a trooper and you hung in there for all this time, I'm going to show you a very special image. Please do not get me in trouble for this, but some of you may know. I always like to have a treat for you that wait towards the end. A little bit of a treat for you. Did you know that some of the faculty members in the psych department play music together on the side? We get together. We get along really well together, and so we decided to start making music together on the weekends. And I'm going to show you a very funny picture. This is from a recent Halloween show where we all dressed up like the members of KISS. I'm not going to tell you who these faculty members are. 3 of the 4 people here are faculty members. But yeah, so this is the Halloween thing that we dressed up for. If you want to learn more, you can go to Instagram.com/JoeTheBand, and Joe is spelled Jeaux, where you can see more very ridiculous things like this. Oh, it doesn't seem to be working, but that's fine. You don't have to see the rest of it. But yeah, so you can find that there, and now you know something about your professors that you didn't know before. Thank you so much for tuning in. If you have any questions though about this really complicated stuff about neuroplasticity, just let me know. I'd be so happy to talk about these things with you in more detail, or if you just were curious about something, I'd be happy to kick around some ideas with you. Thanks for tuning in. I'll see you later. Bye. Sorry, I got distracted because, as you can see, my dog is letting me know that he wants to go outside. I think he's going to try to go under my desk here. All right, so basically